Right, so we are now recording, right? Okay, so we're recording. We're going to continue with our discussion of Fastai and image processing, as you may remember. So I have a question for you guys. In 520, who won the competition? Was it you, David? The Sci-Fi 10 last fall? What did you get on the score? You guys were the highest, right? Joey, Danielle?
I think between the three of us, yeah.
Well-
No, Joey was not. I remember that one. Joey tried to do the
Who was that? Was it
It was
you?
him and I don't.
What did you guys get?
Pull it up.
Yeah, if you can tell me, right? So you guys built a CNN from scratch, right? You were building, playing with it. Okay, so let me know what that score is. So today we're gonna go back to that problem, Sci-Fi 10, but we're gonna apply to it now transfer learning, right? So we're gonna add a little bit to it, just to see if we can obtain better performance. So in 520, for those of you that weren't in that class, we built CNNs from scratch and we trained them on Sci-Fi 10, and then we did a competition, right? And all students participated. And then I believe you guys got the highest score on it, and it took a lot of work, GPUs and everything. We did the 10 class problem, right?
Yeah, my F1 score, the highest for the high average was 0.823.
823. Okay.
Yeah, my average F1 was 0.835.
Okay, so you didn't quite reach 84, right? Neither of you. Okay.
Yeah, some of the runs did, but the average wasn't 84.
Okay. Okay, so you reached, so just give me a value. 84 was your
Like the
the highest, right? Okay. So today I'm gonna show you how now you can take that same problem and we're gonna try to throw transfer learning at it, right? And just motivate that and see if we can start going up somehow, right? So we're gonna do that discussion today with Fastai. So this should be a fun presentation. I'll just do this problem. We're going to code it up with Fastai, and you're going to give it some data from scratch. So literally, you could do this on any image data set that you have. If you have a classification task and it's images, you could use this for classification. All right, so we're using Fastai in a CNN learner. Okay, so let's go ahead and start. So we were recording. Let me just double check it. Yeah, it's my power. I'm very low on power here, but it's plugged in. Okay, all right, so it's charging. All right, so let's start Scholar. And then I will walk you through. I have all the materials already on the GitHub, so you can download them from there. You will need Sci-Fi 10. That's 68 megabytes, I believe. So, you'll need to download that, okay? But it's actually very nice how this works because it's very simple, to reuse this code for any image classification task that you might have for color images. And you're going to throw at it something very powerful. All right, so let me go ahead and start here. All right, so we are in Scholar, so I'm going to go now in a Jupyter Notebook. And I'm going to hit launch. Hopefully I can get one. Okay, great. We got one. So I'm going to go to desktop. I'm going to create a new, I already did it, but you can see I have the data here. I'll explain to you how you can get the data, load it up on Scholar so you can repeat this later on at home or something like that. It's not homework, but you should. I do recommend that you repeat this exercise. Okay, I'm going to go to the GitHub. Okay, so just go to the GitHub here. Go to transfer learning. go to Fastai, and you'll see that I have this. We pretty much covered basics and computer vision in the last previous lectures, right? So we've covered those. Sorry. And now we're going to cover image classification, okay? This will motivate transfer learning, in particular ResNets, right? ResNets is just like GPT, right? We hear all about GPT, GPT-3, GPT-4, right? In text, the analogy in image processing is ResNet, ResNet 18, ResNet, you can keep adding ResNet 128, whatever, right? So that's the idea. So if you click on image classification, you can see that I already added this one, classify Cipher 10 with Fastai, right? So that's basically the Jupyter that I'm going to go over today. You can look at that code. I'll explain how it works, but it's actually very straightforward. And for the data set, I found Cipher 10 in a zip file, so it's very easy to get if you go to this link. So if you click on that, I just downloaded the whole thing, but I ended up just using the train set. Okay, so as you can see, it's got, I think, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 classes, right? For airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. All right, so you can download this data set. I just took, train basically and used it. Okay, so definitely you can use Cipher 10. And I kind of wanted to, because we did it in 520, right? And you guys worked really hard at it, right? I wanted to kind of continue from that, but this time around throw transfer learning at it. And I only threw at it ResNet 18. So in theory, you got more powerful ResNets, right? So the higher that number is, the more layers, the more. Remember, it's a ResNet that's pre-trained, right? So you're bringing in weights just like you do with the GPT-3s and so on, GPT-2. Okay, so that's kind of the motivation. So what I did is I downloaded train, right? And then I zipped it. And then once I zipped it, I went into here. And we have a nice function upload, right? So this is now Scholar, so you can click on upload and then basically follow the prompts. It'll allow you to select that zip file and then you can load it up to, it'll put it on your desktop basically. So you can see that it's right there, train cipher10.zip. Okay, so this gets it into the environment of the Scholar. Okay, so yeah, I'm gonna go back to, because I'll be using the code example. I'm gonna be using my own code, which is this one. Okay, once you are there and you've uploaded the zip file, go to cluster here, remember? Click on cluster, click on Scholar Shell Access. You can hit clear here, always check your quota. So yeah, so kind of the limit. Pwd tells you where you are, so you need to be in desktop. Oh, and then this is my desktop. So then you can see I loaded it here, the zip file, right? Then what you can do, I already unzipped it, but you can just simply type unzip and then train and then, zip like that. When you hit enter, it'll unzip it and everything, and it should generate a file, a folder, this one, train Cipher 10. Okay, I'm not going to repeat it because it does take a while. I actually have to go get some coffee while I was doing this. So it does take a little bit. So once you do that, you'll have your train Cipher 10, so you can CD into it. And I'm going to do it clear. All right, so in 520, this is kind of the technique I showed you also on how to read images, right? So this seems to always be like one way that's kind of very easy to work with images, right? You create a folder, and then if you have 3 classes, let's say apples, bananas, oranges, then you create a folder for apples, one for bananas, one for oranges, and then you put your images in there. And that way, you can just retrieve the name of the folder as the label. Does that make sense? So you'll label your apples, your bananas, your oranges. Okay, so this is how this is done. If you notice, if we do PWD, you can see in the train cipher 10, there are 10 folders. And then if you CD into one of the folders, you can see that basically you have all the images, the JPEGs of airplanes, basically, and things like that. Cipher 10, I believe, is 32 by 32. So I think that's what it is. And that's it. Once you have this, then that's what you need. Okay, that's all you need, the format that you need to put your data set in, right? And then you can proceed to do the analysis. Fastai also handles if the images are of different sizes. So because we're going to use transfer learning, right? In transfer learning, the ResNets, just by default, only accept images that are 228 by 228. That's the maximum. And doesn't allow images bigger than that, or, you know, that's like the optimum. Make sense, guys? So in this case, we don't have a problem, but if you had bigger images, just know, or different sizes, just know that they would all be made into 228 by 228. All right, so I think everyone understands. So now we can proceed to the Jupyter Notebook. So I'm gonna just write it, you know, take this code. I opened this one already, right? So I'm gonna initiate a new Jupyter. I'm using, I ran this on PyTorch, or sorry, Python 3.8. I'm gonna use that. Okay, so I'm gonna do just some cells here. I'm gonna rename this as in class cipher 10. And this is the reality of how things are, right? So you guys have the competition, work really hard, but somebody uses transfer learning, they may beat you, right? And somebody uses a ResNet 18, but then somebody uses a ResNet, you know, 64 or whatever. So they might beat you, right? Because they're using transfer learning, a data set that has been trained, sorry, a neural network, a CNN that has been trained on many, many images. So in class cipher 10, classification. So this should be a pretty complete solution. So like I said, this is I think it's a nice example because any image processing, any image classification task you have, this should get you going and provide exceptional state-of-the-art results, right? So it'll be very difficult for others to beat you unless they have 10,000 GPUs and things like that. All right, so let's go ahead and begin. So this is why transfer learning is so necessary, even though it's great to know how to code from scratch. How many hours did you guys spend trying out those models? A lot, right? Yeah.
Well, a lot of it was just like not even changing much, it's just doing them over and over again to get attitude.
Yeah, and trying it out, and yeah. So regardless of doing, you're always going to be at a disadvantage to transfer learning. That's the reality of it. You go to your job and I'm going to build it from scratch, and you try and try, but if somebody uses transfer learning, they're very likely going to beat you, okay? Because they're leveraging all those weights that have been trained on other models. So that's the idea. I already ran the cipher 10 on this, and I did beat that score of yours, not by much, but significant, by something that I would say is statistically significant. Okay. So, and I only use a ResNet 18. I leave it for you guys to try other ResNets, and maybe you can get into the 9, more. All right. So let's go ahead and get started. So I'm going to grab the libraries here. I already tried all of these. I'll point out, these are the classic ones: Torch, NumPy, sklearn, Torch Vision, Matplotlib. The only one that you may not have is this one, MLXtend. This is a nice library for like visualization, so I recommend that you guys install it, okay? But so let's run that. While it's doing that, I'll copy, this is the command to install MLXtend. Okay, so it ran no problem. Then I'm going to import these libraries here, basically Fastai, right? So Fastai is what we're using now. So yeah, this information. Okay. Okay, so we have the libraries. Now we're going to load the data. So this is usually a very difficult task, right? As you guys are aware. But if you follow this pipeline for classification, I think it should make, this problem almost trivial, right? As long as you put your images in the folders as I described. So I'm going to go ahead, hit markdown, load data. All right, so we went over some of these ideas, so I'm not using anything new. It's basically what I demoed last week. I'm just all of it together. All right, so the first thing is, I copied this from a project I did. Cypher. Okay, so download Cypher with a folder inside for each class, e.g. plain, whatever. All right, so plain, dog, etc. Right? So just like I showed you before, this is what you need to have for this to work seamlessly. Put images in each corresponding folder, basically. Okay. So here we're going to basically put in the path. So in my case, I'm putting in the Scholar path. So, and then the folder train Cypher 10, which contains the 10 individual folders for plain, dog, etc. Okay, so we can go ahead and run that one. Okay, then I'm going to print out these paths. Remember that Cypher 10 does not actually load the images in memory. It just has the paths to them. And that's very efficient, actually, right? Because you only read them when you need them. You don't have to carry an object with all these images. All right, so is currently thinking, and it should print out all the paths. So you can see there, Cypher 10 dog, basically it's just showing for the dog folder and all the individual images in it. Okay. So that, let's save it. All right, so now we're going to create the data loader. And that's what, one thing that's handy about Fastai. I mean, in general, we want to use data loaders in PyTorch, etc. But here we're going to use the data loader for Fastai. Okay, so I'm going to hit that. Now I'm going to load the actual data loader. And I'll go over some of the details. All right, so this is a data loader. Basically, I changed, this is, okay, so it should be Cypher 10. Cypher. So Fastai has these things called data blocks, okay? And it basically, there's several types. So there's one, so just to give you an example of what this means, is there might be a data block for images, but to predict regression values, like to predict the number, like 35, 37. There may be other blocks to predict a class, so that an image and a class. You see, so it's like they've thought of all the scenarios where you could use it, and then they have these available, right? So in this case, I'm using this data block here, and I'm going to use it for classification. So this is where you tell it what your problem is going to be. So in this case, the blocks is tuples of an image and a category. You see that? So like an image of a cat or a dog and the label dog. Okay? So this is basically the format. Then you're going to tell it to get the images. It's going to use this function, get images file. So that's this same one here, right? Which is also a Fastai function. Then you're going to tell it to use a splitter. So you use a Fastai object called a random splitter. And all you specify here is what? What is the size of the train set and the test set? So in this case, it's going to handle everything for you, right? It's going to use 80% of the images for training, 20% of the images for testing. Does that make sense? And it's got the seed value for the randomization of the data. This one is the very nice and handy parent label. So this is basically, you can see I wrote it here, simply gets the name of the folder a file is in. So if it's an image of a dog, right, and it's going to be in the dog folder, so it's going to take that and that's the label. It just does it for you. Remember, we saw this the last time where we had another way of obtaining the label, right? By just looking at the first letter of the file, and if it was uppercase, it was one class. If it was lowercase, it was another one. And we just defined that one. Here, we just use this function as a built-in function of Fastai because this is such a common approach, right? To put your images in the individual folders. Got it? All right, and then if you notice over here, it's got this item transforms. So Fastai uses this idea of transforms, also Torch Vision, etc. You have basically these ideas of transforming your input into something else, like normalizing. We've seen that. In this case, you use the object resize. Okay, so by default, this function will crop. Okay, so if you have bigger images, it'll crop them basically. Okay, so it'll resize, to 128. You can try 228 or whatever, but basically here I'm doing this with 128, and the results are good for CIFAR 10. Okay, go ahead. All right, so the object has been created. Let's continue. Now that the object has been created, I'm going to create the data loader object. So I'm going to do this data loaders. So it's going to have the path base. So it's got and I need to change this name to CIFAR. So now I invoke CIFAR, right? All the details here. And now I load the data basically, right? The data is in path. That's the list of all that we saw over here, right? The folder basically. And once we do this, our data is effectively ready to go. You see that? That's it. That's all it takes with Fastai to be able to process all of our images. Any questions? If this is too small, I've tried this. It'll fail because it expects a lot of data, and so I think it tries to do a batch of like 32 by default or something. And if you give it few images, actually, it won't be able to create a batch. And so it's going to fail out. Okay. All right. So now that I have this defined, DLS, let's keep going. So we can view some of the data, right? And I'll show you some examples of things that you can do to the images, although the effect is not always obvious in these. Say view some of the data. Okay. Run. All right, so now just copy this. All right, so by default, it will give the model batches of 64 for training and testing. So that's kind of like a default parameter. I'm sure you can change it. To view, we're just going to call DLS, and we're going to say valid show batch maximum for n rows 1. We can hit run, and you can see these are the actual images of CIFAR 10, which is probably familiar to you guys from 520. So it's a horse, a cat, a dog, a cat, I guess. Right, so some of these are kind of hard because of the resolution is so small. All right, so let's keep going. Now, some of these, it's not obvious that it's actually padding them, and I think it's because they are the same size. But I still wanted to show you at least an example of the command. So whenever you have other, images, that you can use this. Okay, example of padding the images. So you can see the trick is here. Okay, so instead of cropping the images, we can pad them. So basically, this should be, remember, now we're going back to not DLS, but the original CIFAR, right? The original definition, the data block, data loader. So I'm going to say here, CIFAR. equals cipher. So basically I'm taking the original cipher, but I'm going to modify it a little bit. Like that. So here, item transform, resize 128, but you also specify a resize method, which is going to be padding instead of cropping. Okay. So that, and pad is 0. So you can specify parameters if you want to do that. If you don't, cropping obviously loses information from the image. Padding doesn't lose information, but you're going to have like, black space surrounding the image, things like that. Does that make sense? All right. So while this, basically, I don't see any effect, but I think it's because the images are the same size, basically. So there's nothing to pad. I did try these other images, and I was getting like a black border around some of them. Okay. You can, and then I'll just show this. I'm not going to repeat it because it's not really relevant to the task, but you can do other things like squishing images. So here, notice all you change is the resize method to squish, right? So you can try other types of resizing, basically. All right. Random cropping of an image. So random cropping of an image is considered better. So why would that be considered better? Because it reflects like reality. It's like you have an image, but you just take like a picture of it and then another picture of it. You see that? So you show a part of it, the top part of it, the bottom part of it. You can duplicate them where one has the top part, one has the bottom. And it's more like the real world in a sense. So you can use something like that. So these are just, this is just a scale. You can play with the scale, 0.3, 0.5, etc. This one I will do, other data augmentation. So these are interesting because it's the same idea as like you kind of like take an image and rotate it or do something to it, flip it like that. It's data augmentation, right? Creating new images from the original ones, but modifying them a little bit, with some transformations. So in this case, I'll do this one. So other data augmentation. So these are things you can play with. Okay, so here's an example. Okay. All right, so this one, data augmentation, basically is a set of operations. So you have rotation, flipping, perspective warping, contrast and brightness changes, all manner of all image processing probably that you can think of. These are just some examples you can throw at it. Because this might be intensive, you want to do this via the GPU. So this function is optimized actually to use your GPU for the augmentation as well, all right? Once again, I need to change this to cipher. Okay, so you can see here, cipher new, you take the original one and you change the transformations to be augment transforms. You can specify, this parameter here. I will play with it a little bit. I think it's the number of transformations it does. Here I'm going to do cipher, the path, right? And now let's run this. So it takes a bit, as you can see, and these are birds originally. But notice that it manipulates them, right? You can see that they're all a little bit different. Do you see that? And basically, it's recommended to do this, or at least to try it, right? When you're building a classifier for images. Do you guys see that? Like this one's like stretched maybe a little bit. This is obviously the colors have been highlighted. Do you guys see that? Yeah. So this is another technique that you can try, right? So These are very powerful. Okay. So let's keep going. Now, I showed you kind of some examples of how that can be done. You guys can try it. But let's get back to the task. So the task is to classify Sci-Far 10. So this is actually the heart of the whole thing. So I'm gonna do this. Okay. Okay, so. And this uses a ResNet, which is the transfer learning. So I'll just say transfer learning is because of ResNet. Okay. And we'll discuss ResNet later, right? In the next lecture after spring break, we'll go over actually just a little bit of the theory of how that works, but I'm not going to cover any theory today. All right, so let's kind of think about this. I'm going to run the markdown. All right, so what are we going to do? We are going to fine-tune a pre-trained image classifier. In this case, just like before we would grab a GPT-2 and fine-tune it for a specific task. Now we're going to grab a ResNet 18 in this case and fine-tune it for a specific class, right? So that's a pre-trained model, right? So here we use a CNN learner. So that's another thing we're going to use, right? So if you remember, we had generic learners, and we can also just use the CNN learner based on a ResNet 18. This is actually a small one. So you could always try more powerful ResNets. This is based on CNN's convolutional neural networks, which we covered in 520. So if you guys have curiosity in that. And as I said, the transfer learning part is this ResNet. All right, so let's go ahead and now implement the code for the fine tuning. As you can see, Fastai makes basically 7 lines of code, right? Can't beat that. All right, so how many lines of code did you guys have? Right, so that's the whole point, right? That's the whole beauty of 520 and then 530, and you're like, okay. All right, so now fine-tune CNN learner with our data. So I'm going to call this now, this is actually the official one now, Sci-Far 10. Sci-Far 10. Notice it's going to do random size crop to 224 now. 224 is the value that you always see in the papers. Minimum scale, so I think it's the downsampling that it uses is 0.5, so you can play with this. This is the item transforms, and it's gonna do augmentations, right? So that's basically what we're specifying here. So then we invoke Sci-Far here. Sci-Far. Okay, data loader's path, DLS. And now notice here from Fastai, we're going to use the CNN learner. This is like the wrapper around the training. Notice that we give to it the DLS, which is the data. We give to it right here, ResNet 18. This is where we can specify which ResNet to use. Does that make sense, guys? And the metric that it uses is basically error rate. However, this collects the data actually. So we can later on extract that object to print out like our familiar F measures and so on, so we can compare to your results. All right. Yeah, and you can see I have commented out some other things. And then finally, we're going to do learn, fine tune for epochs, right? So you could do more epochs. I only tried this. It didn't take long. And I was happy that I had something higher than I remembered you guys. I thought you guys were in 82, but all right, so I'm gonna go ahead and run it. So at this point, it is actually training. Remember, this does need a GPU. All right, otherwise it would take a very long time. But we are in fact at this point fine-tuning our ResNet. In essence, here you probably have ResNet 18, right? And then maybe it adds 2 or 3 layers, right? And those are the layers that we're fine tuning. You don't want to change the original 18 layers. Later on, we're going to think about the algorithm of ResNet, but the intuition is that those 18 layers are really good at feature extraction. Do you see what I'm saying? Like, if you remember, CNNs are about applying filters to an image to produce new versions of that image. You guys, that's kind of the intuition of a CNN. And so those filters are now populated by learning the weights, right? So it's got really good filters, which means it's really good at extracting edges, right? Eyes, fur, all, machine looking things. And so that's the power of something like ResNet. It's the feature extraction, basically. Okay. So that's the intuition. So it's currently training, and remember, our objective is for the losses to go down, right? So that's kind of what we are going to be interested in doing. So we're going to let it train. Obviously, if I had a bigger ResNet, maybe I would have gotten better results, but also the training time would have taken too long for the class. This shouldn't take that long, I don't think. Any questions while it's doing this? Sorry? Why? Is my stomach rumbling or something? No, I eat after class.
I always wonder, like, I wonder if our professors do. Like, say, like, Professor Kim, like, all those classes, I can just.
It's almost like a different lifestyle. I agree with you. A very sad, painful lifestyle. Yeah, I agree with you. I often think about that too. So you can see the losses going down, right? So 0.81 to 0.64, 0.54 to 0.43, right? This one's going down, this one's going down. So actually, this is great. I mean, this is a very well-studied data set, so it's very stable in how it performs. Other data sets, as you probably have seen, go up, down, that kind of thing. All right. I think it's only doing 4 epochs, right? So it should be done soon. All right, so I think it finished. So there we go. All right, so we've fine-tuned basically our ResNet for this task of identifying the 10 classes. You see that? And basically, you could do this for any image classification problem you have, right? Images of any size. So very powerful. All right, so let's go ahead now and evaluate it. So there's actually quite a bit for this. So the first thing we're going to take a look at is the confusion matrix, right? So you guys probably very familiar with that one. It's usually something that, you want to look at. Go ahead and hit mark down. All right, so that's confusion matrix. All right, so it's going to process that. That is saved in Fastai, right? So we are just grabbing it from there, from learn. So we are invoking this thing called classification interpretation, right? And notice we just passed to it learn. And what is learn? Learn is just our object, our Fastai learner. Got it? All right, so let's take a look at the confusion matrix. So it's kind of small, but you can see it's that. What do you think? The model's doing well, right? Because all the values need to be on the diagonal. It does have some errors. I was looking at these errors. It seems to be cat, probably because it's confusing it with other animals. That seemed to be one of the most problematic ones. Dog, maybe. Right? So, but otherwise it's pretty good. So it's always good when you have a multi-class problem to look at the individual performance per class. Although for the competition, as we did, we were just looking at one score. Right? So so that's kind of the idea. All right, I'm gonna show just a bigger version of the confusion matrix. Okay. I'm gonna use that interp object. Okay, so let's go ahead. So this one looks more professional. So if you're writing a paper or something, this one is kind of nicer for you to like save and present. Right, you can see here it's got the classes already, and it actually highlights. So it's a bit of, well, the other one does that too. But they're kind of highlighting the maximum errors. It's like a heat map, right? Heat map. All right. So, but what you guys care about probably is you want to know the scores, right? So let's take a look at that next. So let's go ahead and ML performance metrics. Copy that. Okay, so ML performance metrics, and we're going to run that. Okay, so notice here from learn, right? We're going to get the prediction so that this is just Fastai has this stored, and we want to get this data. So we're going to get the preds, the Y, so basically the predicted and the real, and the losses associated with them. Okay, so that's what we're doing. Just going to give it a minute there. All right, so we've got that process. Now we can go ahead and these. All right, so we're going to print the shapes and get the values, the Y preds. Okay, so from preds, we use torch argmax, right, as usual, and just extract the prediction. So we have 10,000 of them. That's the size of the Y pred vector. Y dot shape, I think I already printed that. Okay. So now I'm just going to use our standard, I'm going to use our standard from sklearn functions, right, to just print out the metrics. So I kind of always like to consistently use just something, right? So this is actually apples to apples. I think you guys were using also the sklearn metrics, although it wouldn't matter, but just in the sake of. All right, so we take the Ys and the Y preds, when we make them into NumPy, we take the accuracy score, which if you remember, this is just from sklearn, is how to calculate the accuracy score. And I also, from sklearn, use the F1 score, which is really the metric that you want to use to evaluate. So we're going to compare here the real to the predicted. We use this method weighted, and we are going to print the results. Transfer learning. Yeah.
Doesn't compare to time, like being put into training.
The amount of time it took you guys to train was longer?
Like just like figuring out like the algorithm.
Oh yeah, of course. Right.
This is like
Yes.
just do it.
And actually we're going to talk about that because ResNet wasn't made by just one person. It was made over 10 years in competition, trying different architectures, different training schemes until eventually they arrived at like the perfect ResNet. Do you guys see that? And so that's kind of what it took. So basically the work that you did is kind of like it would have been used the next time around to improve your CNN. And the next time around, they would use the previous ones and so on until eventually you arrive at, okay, the optimal architecture is, you know, these many layers with these many neurons and these normalizations and so on, right? And train on this data, pre-train on this data. So it took a long time. I mean, you know, it wasn't just done in a day. But yeah, so as you can see, this achieves 88% F1 score and accuracy actually very consistently. So there you go. Transfer learning gives you this power, and you know, for instance, in this example, you guys took 520, learned how to build CNNs from scratch, worked really hard at it on Sci-Fi and achieve 82, 84. In 530, you've learned that transfer learning is a new thing. Now you use transfer learning, and it's taken your score from 80, a maximum of 84 for the winner of the competition, to 88 by not doing much in terms of time, as you said, and just a few lines of code. Does that make sense? So this is what, if anything, like if of the whole class, this is one lesson you need to take with you, right? That, yeah, it's great. You should always know how things work, PyTorch, but also don't ignore these frameworks like transformers or Fastai because they're using transfer learning. So it's almost like you're building on the shoulders of giants, that expression, right? Or, you know, you have Fastai is providing you a team of 10 additional data scientists that are helping you out to build this better CNN. But also, you should know how things work because sometimes you got to tweak things, right? You got to understand how the data will impact the, you know, the algorithm, the ResNet or whatever. You see, so it's both, in my opinion. That's my opinion. So understand everything as much as possible and know that, but also know how to use these frameworks, know how to use transfer learning. Don't neglect either one. It's just the nature of how it is today, right? Any questions, guys? We're not done, but I wanted to show you this is, you know, ultimately, as you know, in machine learning, this is how it works. You provide the performance. Seems like it's clear. All right, so let's just keep going. So we achieve 88%. As I said, if I wanted to improve this, what would be the first thing I could do? Well, possibly more iterations. We might want to try that. But also this here, right, is probably the key. Trying other ResNets, right, that might be more powerful. What do they have? They're deeper. You know, deeper more means more layers. Does that mean that they understand even more about the images? Possibly, right? So that's what you want to try. If you were in a competition, if you do ResNet 18, someone's going to try a bigger ResNet. All right, anyway, so hopefully that, I think this exercise captures this whole transfer learning concept really well. So let's keep going. So I printed this, right? So actually, this was a little bit better than what I got this afternoon. This afternoon, I got 87. Okay. So a couple of more things that the learner can give you that are very handy. As I said, remember that I'm saying to you, you're going to have a problem. You want to use this tool. Joey, when you guys did the thing for that paper, did you use Fastai?
Yeah, we use Fastai and ResNet 50.
50, yeah. So yeah. So when you have a problem, any kind of problem, you know, you might want to use something like this. Okay. All right. So here you would have labels, you know, for whatever problem you're doing. So then you want to print them out, right? So you want to get that information out. So this is how you can get it easily. Okay. All right, here are the individual scores, which is something that you always want to look at because this can also give you insight into what's causing the problem, right? So we can analyze this one. Right, I'll add a few more cells. All right, so if we take a look at this, we can quickly know what do we see there? The data set is that, okay, let me ask you some questions. Is the data set balanced or imbalanced? It's balanced, yeah. It doesn't need to be perfect. That's balanced to me. Imbalance would be that one of those is like 20, you know what I mean? That's enough. But otherwise, this is balanced data set. Then we got our precision recall and F1 measure there. We got the average, which was 88.88. So what are the troubled ones there? Let me see. Probably 3, right? 3 and also, well, 3 mainly. Yeah, that's probably the cat one. So we're gonna, but we want to see that, right? You're writing a report for someone. The first thing we're gonna say is what is 3. So you want to, do it a little bit more better. So we can do that simply. We already have the vocabulary here, so we can reprint this probably with this approach and add the labels in there so that we can do a better analysis. We can go ahead and hit run. All right, so now we have the labels, right? For whatever, and the nice thing about this code is that it works for whatever problem you have. You just dump the folder with your images and everything else will work. So in this case, we know that the problematic one, the easiest one to classify is probably automobile, which is surprising to me actually. The hardest one is cat, deer, oh no, dog, cat and dog, right? 75 F measure and 81 F measure. Do you guys see that? Yeah, so if you were doing something, this is probably where you want to go in and kind of do, figure out what, if there's anything at all that you can do to fix it. But anyway, overall, the scores are pretty good. Most are 90s, 88, 85, I guess, and so on. So this is a nice, for data science, this is a nice little chart. All right, let's save that. All right, so let's keep going. All right, so we're going to plot some of the parameters just to get some ideas of the predictions. Okay. Okay, so plot some losses. All right, so plot some losses, show us the images with the highest loss in our data set. Okay. All right, so this shows misclassifications, basically. You can see, actually, I was doing this, I was looking at these images this afternoon. Let's see if you guys see what I see. All right, so for the first image, the first word should be the prediction, and then the next one should be the actual, right? So this is supposed to be a bird, but it was predicted as a truck, right? However, what is that red thing under the bird? It looks like a vehicle, right? I think it's probably a bird on a toy Jeep or something, is what I assume. So yeah, that's why it got confused. It thinks it's a truck. I mean, there's a truck, right? Is that what you guys also see? Yeah. This one, cat versus deer, that literally looks like a cat to me. Yeah. Yeah, then if you look closely, it's more of a deer, I suppose. Yeah. So yeah, so it kind of makes sense. Okay, truck, automobile, so that's, it's still predicted a vehicle, right? It's just maybe a subjective kind of a problem. That, it's supposed to be a deer, but it predicted a frog. That looked to me like a frog leaping or something.
It sounds a little.
It-
Sounds a little more
it
difficult.
looks like what?
It looks like-
A deer drink. Ah, I see it now. I see it now. I just saw it. Yeah. I thought initially it looked like 2 legs, so like jumping.
Yeah, if you were like looking at it symmetrically from like the reflection in the.
Yeah.
You could.
But I see it now. Here's the head. ears and it's drinking water there. So yeah, I didn't see that before. So there you go. Yeah. So those were, if they're subjective to humans, obviously they're going to be difficult for a computer. Got it? All right. So yeah, so that's kind of what we can get with this. So you can see this provides a lot of power, right? For your analysis, all those kinds of things. So that's, the beauty of this tool. All right, so we're done with that part. So now what you might want to do is you want to use this model as inference, right? So remember that in transfer learning, it's all about ChatGPT, right? So you have a thing and now you're going to deploy it to a hub or use it because it takes so long to fine tune, et cetera, right? If we were doing this with massive amounts of data, right? So, so in this case, the learner from Fastai has a very nice function to save the checkpoint so that you can share it with your friends or just use it for inference later on, right? So this function will save and export export a file called export.pkl to save this model. So all you have to do is learn.export scifar10 models labels 2. I'm going to go ahead and do that. And that's it. Model checkpoint saved. Now you can go build an application with this. Okay. All right. So now let's take a look at in 520, we saw how to do this with Onyx, correct? If you remember how to deploy things with Onyx. I haven't looked into the connection of Onyx and Fastai. But you guys may, if you want, look at that. My feeling with that is that the models are going to be big, right? So you need to deploy it on your own cloud or something. But otherwise, it should be doable. I know that I've seen Transformers has a Onyx connection, so probably to deploy some chatbots or something like that. All right, so we exported the file. Now we want to go ahead and import it. So I'm going to, assume I have another application over here, right? So this is now the function to load something that you train in Fastai back into Fastai. I'm going to call this one, if you notice, I'm going to give it a different name. Just learn_in for inference. And we're going to load the learner's scifar10 model labels PKL. So I'm going to hit run, and that's it. You're done. So now you share the model with your friends or your team, and they can start developing, whatever is necessary. All right. So now we're going to test these models, and we're going to see that they both should work. So I already grabbed an image. I'm going to grab a different one. So I just copied dog 1428. Well, I think it was the last one. So now I'm going to grab the first one. Still a dog. But you guys can try different files that you want. I mean, in theory, Okay, so I'm going to go here. Oh, here. I'm going to, I'm going to replace this with the new file. All right, so 3879, that's my image. Notice that all you have to do is give it the path to learn.predict. And it's gonna, this is just a variable. So I just copied this code, but basically it's gonna tell us the label there. Okay, so this is like the class. So you can just go ahead and run this script. And it predicted that it's a dog, basically, which should be. You can see here, these are what are these called? The logits, right? So if you remember, so the highest logit is this one. So this again takes us back to just as an analogy for RLHF, right? You're building a reward BERT, which is basically a classifier. Remember that although it predicts a class, they always produce logits, right? So this produces a vector of size 10 for the 10 classes, where each one has like the probability that it is that class. And because it's probably softmax, these should add up to 1. Okay, so then we said in the reward model, you just grab one of these consistently, and that's your reward model, right? So that's the same idea. All right, so for this one, I used learn predict. Now I'm going to repeat the exercise, but with the learn inf. So basically the model checkpoint that I just read back in. Okay, I'm going to go ahead and run that one. And it should give us the same, as they are the same model. Okay, so run that again, and there you go. It gives you a dog, basically the same logic and everything. So using the actual learner and the one from the checkpoint, basically. Any questions, guys? So you can predict your classes there, no problem. Okay. So I had done this vocabulary here, so just for consistency. Okay, I'm gonna also, I think I just wanted to show the classes. All right, so let's see. We want to look at that image, right? So we can just do something like this. All right, so this should be a dog. Is that a dog? Some type of a dog, I think. Like a sheepdog, Shetland sheepdog, right? So yeah, there you go. Okay, we can also print some of the predictions to show some results here. Just so that we get a feel for what's going on. This is after the model has been trained. So these are like predictions. So we can see where it's kind of erroring out. So this is a deer, and it predicted a deer, a truck, deer, and predicted a cat, probably. This is an airplane, predicted an airplane, horse, automobile, predicted a ship, horse. That definitely is a cat. Right? So you see that, so you can see the predictions and get a feel for where it's erroring out. This is kind of like default settings. We can also say maximum number of images, so give it a little bit more flexibility. So let's try that. So here we have 10 images, and you can see the results, basically, of the predictions. Any questions? Does this make sense? So there you go. So I haven't given you an assignment yet for this. I don't think I'm going to give you this assignment. It's very straightforward, honestly. And instead, the assignment I'm going to give you is going to be conditional GANs, which will be a lot more fun, generative models, right? So this should be trivial, hopefully, and hopefully you have a nice tool. So no homework for this one. Instead, I just want you to finish the mini project, right? Which is due the week after spring break, right? And then after that, definitely, I will continue next week with this topic, ResNets and CNNs, and then GANs. So we're going to do a quick review of GANs, and then we're going to get, which we did cover in 520, but I didn't cover CGANs. So it'll just be like a quick review of GANs, and really the assignment will be CGANs, conditional GANs, okay? So what I want you to do there is to generate images, but you're not just going to generate random images, you're going to give it like a class. Like I'm going to say, I want you to, in the example I'll give you, I'll say I generate a 7. So then you have to generate 7s or a 3. But this is going to be the homework will be, each of you are going to use different data sets for this problem. Got it? So we'll go over that. So I'll go over how to do that, the pre-training, and then maybe you can even leverage transfer learning for that. And just, that will be a homework, possibly not the project, the last mini project, which is, I'm still thinking about that. Still have time. All right, this kind of concludes this lecture. Okay, so are there any questions? Questions? So we still are going to cover a few things like object detection with YOLO a little bit. GANs, as I said, the art transfer thing. So just a few ideas of things that you can do in this space. Okay. All right. So I'm going to go ahead and stop. I'm going to stop the recording here.